let's take it step by step. The first question is, why are we looking for dimensions of the greatest variance? Why is that a good thing? So suppose I have a little two-dimensional data set. These are just a set of points. Ignore the colors for now. And suppose that I'm looking to reduce the dimensionality. So I'm trying to embed these two-dimensional points in a one-dimensional space. So I'm only going to have one dimension, a line. I'm going to call that line E. And let's see what happens when I use different dimensions to project my data to. So I might have the blue dimension E, right? That's the dimension along which the data is spread out the most, or a green dimension. Along this dimension the data is not spread out. By the way, what do I mean by spread out? Suppose I'm looking at the blue dimension. What I'm going to do is if I identified the blue dimension as what I'm going to be using, I'm going to project all my data points to that dimension. And projection is basically just dropping a perpendicular line from each point to that dimension. So I'm going to end up with a set of points along the line, right? And you can measure variance, how varied the data is along the line, just by looking how spread out the points are. Right. So the projection points are pretty spread out along the blue dimension, and they're bunched up along the green dimension. So you would say that the variance along the blue dimension is higher than the variance along the green dimension. Now, why is it good to have high variance along a projected dimension? Look at the two red points. They're pretty far away from each other in the two-dimensional space. If I happened to project them to the green dimension, those two red points end up being on top of each other. So this dimension does not preserve distances in the original space. I had 2 points that were very far away in the original space, and after projection they ended up being very close to each other. And remember, distances are important. They're really the basis for all of our learning algorithms. So you don't want to mess around with the distances too much. If points were far away, you would like them to still be far away in the reduced space. So if you're projecting to the blue line, yes, they're going to still be pretty far away. Now, that's not going to happen for all points. When you're reducing dimensionality, you are forcing your data into a lower dimensional space, so necessarily some points that were pretty far away will end up being close to each other. So, for example, that point and that point are going to be pretty close to each other. But if you pick a dimension with the highest variance, you're going to minimize the number of those cases where points were really, really far away and ended up being very close together.